because I'm not giving away our answers to the exam. So the last thing we talked about was the charge balance equation. We said we were introducing a couple of different types of equations. You want to click on something in a moment. Click your manual.
You want this back, right?
I do want the test back before you leave today. Yeah, you want to continue to look at it for a minute, but yes, before you walk out of the room, you're going to give me the test back. Okay, so we've got the the charge balance equation was an equation that gives us basically charge neutrality for a solution. The summation of the positive charges has to equal the summation of the negative charges for a system. We looked at an application of that, so let me, I worked this one in the notes. So on this one, I want to write the mass balance and I'm going to do the charge balance equation for this example. So this one is lanthanum phosphate. Lanthanum phosphate is actually one of the ways that we get rid of phosphates in samples. So like if you're doing an analysis of milk and you're doing the calcium analysis of milk, calcium phosphate is not very soluble. So it'll cause the calcium in milk to precipitate out. So what you have to do is get rid of the phosphate in milk so you can analyze the calcium ion free. The way that we accomplish that is we throw some lanthanum in there. And lanthanum will bind very, very strongly with phosphate because they're both highly charged ions. They pair together pretty well. Okay, so if I think about this guy and I have to realize what are the charges associated with ions, it's going to associate, a big pen, much bigger than I want. It's going to dissociate into the lanthanum cation and the phosphate ion. All right, so now the question is, what are the ratios? Now I know the ratios by looking at this, but also have to know the charges. All right, so what is the charge of the phosphate ions? You got to know your polyatomic ions. All right, it's a -3. So what does that mean the charge has to be on the lanthanum? It's got to be a +2. So to write these equations successfully, you've got to know that. Okay, you got to be able to do those charges. So the mass balance equation would relate those two things. So lanthanum is not going to react with anything else. So 3 times the lanthanum is going to equal to 2 times the concentration of the phosphate. But I'm going to put a T behind that because phosphate is a base. So phosphate can actually be in multiple forms. It can be fully protonated in the form of phosphoric acid. It can be diprotonated in dihydrogen phosphate. It can be monoprotonated. And then finally, it can be in the form where it dissociates the fully deprotonated phosphate ion. So I have to take into account that there are 4 different forms of phosphate that can coexist here and will coexist. It doesn't matter what form of phosphate I put in. If I start with any of these 4 species, all 4 of those are going to coexist in equilibrium. That's what equilibriums are. So now this relates all of those species. All right, so did I do that right? This is the tricky. 3 times the lanthanum, 2 times the phosphate. There's more phosphate. Okay. You got to think about this one. The lanthanum concentration is higher than the phosphate concentration. because of the association. So it's 2 times the lanthanum is 3 times the phosphate. So you just can't take the stoichiometries. You have to switch the stoichiometries. So this stoichiometry actually has to pair with this one. This one has to go over here. That's tricky. All right, so this would be the mass balance equation. That's a hard one. Charge balance equation is much simpler. Charge balance equation starts off with the autopyrolysis of water. And you put all the positive charge species on one side and all the negatives on the other. So positive charge species, there's only one. And it's the lanthanum cation. And it's a 2+ cation, we said, so you simply put a 2 in front of it because of the charge. And then you put all the negatively charged species on the side with the hydroxide. So the negatively charged species I have the monohydrogen or dihydrogen phosphate, which is a -1 charge. I have monohydrogen phosphate, which is a -2, which means I need a 2 in front of it. And then I have the fully deprotonated phosphate ion, which is a -3, so it needs a 3 in front of it. That gives me charge neutrality. If I sum all those together, positive and negative, that allows that solution to be electrically neutral. Okay? So, key thing about charge balance equations, there's only one. It has to encompass everything. Where mass balance equations, you may write several mass balance equations for a system.
I have a question. Why didn't we use the H3O2?
It's not charged.
It's not charged, exactly. It's neutral, electrically neutral. It only use charged cation.
Okay.
Yep. Or charged species, not just cation.
Talk about why you switch the subject there.
Okay, let's look at something simpler, and it's easier to see. So let me insert a blank page. Let's say that I dissociate this guy. Now, sulfide's actually a weak base, and that'll shift to form some bisulfite and some hydrogen sulfide. But let's pretend that's not going to occur. Let's say it's this simple. Look, that's a special. I got a special sodium there. Let's try to get the right charge on the guy. Oh, 1+. So if I look at the relationship between these two, which one has the higher concentration? The sodium or the sulfide?
Sodium.
The sodium. So that means if I'm going to write their concentrations, the sodium is equal to the sulfide concentration times 2.
Okay.
That's what we're doing here when we write the mass balance equation. Does that make sense?
Yeah.
When you look at something that simple. Okay, so that's what we're doing. We're relating concentrations.
Do we ever have a species that dissociates 3?
Say again?
Do we ever have a species that'll disassociate 3 different things?
Well, this example in reality is 3 different things because sulfide is coupled to
Because we're at aqueous environment.
Yep. If this is in water, you can't have one without the others. It's the same way with the phosphate.
Still something to.
But overall, there's the same amount of sulfur, right?
Yes. So all of those would have to be summed together. That's mass balance. So that 2 would be distributed to every one of those terms. Okay? All right, you got to have Alma here today. Question? Or you wouldn't be here. Oh, that's wrong. What the heck?
What are we going with here?
Well, it's entirely possible that that's not true, that that's not correct.
Boy, that would be-
Or-
Do you trust me?
Social. No.
I like that.
Try and actually work
Right.
it out.
I like that. Like this train of thought. Press that check mark. All right, so let's see. Nobody's voted. Yeah, they are. Sorry. That's an 8. Okay, we're all in. A couple people didn't trust my check mark.
Oh, wow.
Okay, so charge balance equation needs to relate all the positive and the negative charge species. So if I look at the start of the charge balance equation, needs to have OH minus and H plus, the autopolysis of water. Okay, that's the species I have here. All right, what about the water? Where does it fit in it? Which side? Then because it's neutral, right? The calcium is going to go with the side of the proton, so it goes on this side. Because of the 2 charge, it has a 2 in front of it. The potassium goes on the side with the proton. It's there. What about this guy? Where's it go? Neutral. So neutral molecules don't appear. The dichromate goes on the side with the hydroxide, 2 in front of it because of the 2 charge. The chloride. So yeah, I just forgot to cover that one up. So I wasn't trying to trick you. But that's a critical equation, and you got to figure out how to write. Okay, it's the charge balance equation. Put all the positive charges on one side, all the negative charges on the other side, and whatever the charge is, you put in front of it as a coefficient. Okay? All right. So we did this one already in class. So our goal is to come up with these systems of equations where we have more equations than we have unknowns, and we're going to learn to do those, write some of these guys out. We can simplify some of these equations using approximations, but we can only do approximations to the mass balance and charge balance equation because they're the only things that have addition or subtractions. The equilibrium expressions, all of the K's we can write, are all products and divisions. So we can't simplify those. Can't drop a term out. And then the other thing I told you in the video is you're going to try to learn how to do some of these things with approximations. Sometimes it's not obvious what's the right one to do. So you have to take a guess. The key thing, if you check your approximation that you make, it's going to show you if you made a mistake or not. So you take a guess and you go. All right, I've already solved this one once this semester, but I'm going to go back and show you how to set it up again, just based on what we've learned. So in this one, it was looking at the pH of this solution. So quickly looking at it, so it's a strong acid. HCl is going to dissociate 100%. Into the H+, and convention tells me that pH is equal to the negative log of the concentration of the strong acid. So if I put in the negative log of the concentration, I get pH 8 and say that's the right answer. Problem is, I know that's not the right answer because I've added an acid to water and it's acidic. Can't be. So what's happening here is that the autopolysis of water is playing a role. So that dissociation is coupled to the autopolysis of water. Now, when I developed these equations before, you may not have clearly understood what was going on. But now I hope you're there. So this is the KW expression. I've got an equation for KW. It says KW is equal to H plus times OH minus, and I know the value of KW. It's 1.0 times 10 to the minus 14th at 25 degrees. The other equation that I can write for every solution is the charge balance equation. So the charge balance equation is going to start with the autopyrolysis of water. And the only other ion that's in this solution is the chloride ion. Now in this case, I know the concentration of the chloride because if this is 1 times 10 to the minus 8th, this is 1 times 10 to the minus 8th. It's not an unknown for me. So the charge balance equation becomes H plus equals OH plus 1.0 times 10 to the minus 8th. All right, so if you know the concentration of an ion, put it in its concentration in the equation. So to develop the quadratic as we did for this, I took 1 and rearranged it for the OH minus. It's equal to KW divided by H plus. And I substitute that into the equation below. H plus equals to, and KW is 1.0 times 10 to the minus 14th divided by H plus 1 times 10 to the minus 8th. And we just got to start learning to look at equations and say, okay, I've got something that's x on this side. I've got 1 over x on the other side plus something. All right. That's a quadratic. So when I multiply this out to get out all the things, it drops down into an equation in the form of ax squared plus bx plus c equals 0. That's a quadratic equation. And that's the one that I solved in the notes earlier in the year.
So that problem only had one unknown.
Only hydrogen ion concentration.
So that's why you get the equations.
Yeah, 2 equations, 2 unknowns. Well, it was 2 equations, 2 unknowns, but we eliminated the OH minus by converting it in terms of the H plus. So originally, if I looked at the series of equations, I had 2 equations. I had OH minus and H plus. But the chloride was known, so it's not really an unknown in the system. So I combined the 2 equations together by taking one of the variables, solving it in terms of the other one, and substituted it in for the OH minus. Okay. I'm combining equations, doing a little algebra, getting rid of the unknown, solving the quadratic. Okay, so we're going to look at these couple of systems as we go forwards. These problems take a while to work. I did a few of these in the videos. I'm going to work different ones in class. The key thing that I'll tell you to when you're looking at these problems is be able to write the equations out. If you can write out the proper series of equations, the equilibriums that are occurring, the KSPs are with them, the mass balance equation, charge balance equation, regardless of your ability to do the math, I'm going to give you half the points. Okay, because I know in the real world, that's the challenge, is coming up with a series of equations. Today we can use Mathematica or one of the many other programs that are available to do the math for you. All right, I want you to understand the equilibriums and words. All right, any questions?
You know, you did say the other day that Mathematica was free for students.
It is, yep.
How would we go about getting that?
If you go to I think it's the help desk page, it tells you how you download it and register your account. It has to be registered with a student email. But yeah, Mathematica, my personal copy of Mathematica cost me $1,000. The one that's in my office. And now they have a damn site license for the thing that I get it for free. But at the time when I bought it, I used to use it for research a lot 20 years ago. And it cost me $1,000 20 years ago. I don't know what it would cost today.
I googled SOSU help desk, click on the first result, and then Mathematica links to right.
There you go.
Okay. Google.
Yeah, it's that thing I tell you, we're not going to use it that much. If you set up your systems of equations, you can go down to the computer lab and you can do this next homework assignment. We didn't get to the point where I wanted to, and you can do it in an hour. you don't have to go to the trouble of installing it at home. Man, I'll tell you is that it's great to be able to check your math. Once you learn how to do this to solve systems of equations, once I got that quadratic, instead of solving it, I wouldn't solve it myself if I was sitting at my desk and solve quadratic anymore. I can use the solve function of Mathematica and type it in 20 seconds and get a solution. There's a simpler program called Wolfram Alpha. It's a web-based thing. It'll do the same thing, same company. But Wolfram Alpha only gives you 5 solutions and it cuts you off. That's all for today. It's solved 5 things for you. Y'all have a good fall break. If you haven't turned that report in, okay, get that turned in before you leave for the break. So yeah, throw the test up here.
Answer for how much? It should be approximately 8 ounces, right?
Of what now?
Of the,
It's a serving, is 8 ounces, yes.
is it like how much you should get in allowance? I already turned them all out, so.
Well, I think I asked you how many ounces would you have to get the 60 milligrams. So,
Are most of them about 8 ounces?
well, it depends on, the 3 different juices all had different levels of vitamin C. One was 100%, so it should have been 8 ounces, or 240 milliliters is 8 ounces. The other ones were like 130 and 100%. So it just depends on,
Anymore.
yeah.
Yeah, I was just wondering because I was worried about my math on one of them.
Yeah.
And I was like, well, that makes, when I got to the end, I was like, well, that makes sense, maybe. So, we'll see.
Did you figure your problem out?
No, okay, so I understand how you do it. So
Yeah.
the question on the test, I got that, and I understand how to convert it. So it's just, did you say at different parts of different parts of the titration? Do you want because I was thinking that you wanted the amount consumed before we added the starch and after. Do you just want one amount consumed?
Well, I just want the questions are specifically asked in order for what you need to do to come up with the answer for the moles of triodide
Okay.
that reacted with the vitamin C. So on that particular question, I just want to know how much of the thiosulfate was consumed with the excess triodide. So that's all I
So
need to know.
just in each titration. So basically how much we titrated out of our urine.
Exactly.
Okay.
Yep.
I think I was just overcomplicating it because it just, you're just talking about the total amount in each titration.
Yeah. Concentration
Okay.
times volume. And then, yep.
Yeah, I think there was just,
The question behind that is use the stoichiometry. How many moles of triodide is that?
okay, and we're going to do that for each replicant.
Yes.
I got you. I guess I was thinking you wanted 2 different values for before and after the starch was added.
No.
Yeah.
All right.
You said you made a